everybody, welcome to today's COSI seminar. This is the last seminar of the semester. We have the pleasure of having Rick Morrison here for today. Rick Morrison is part owner and research member at Distant Focus Corporation. He received his bachelor degree in physics from Iowa State University and his PhD in physics from Yale. And he then went to work at Bell Labs until he decided to found this company. He started working there in this company in 2001. And his current interests include developing folded imager optics and computational imaging platforms. So, welcome.
Thank you. Thank you. Let me go back 1 second, and you may have noticed I didn't mention a master's. I do have a master's. I usually don't mention it because it's a Master of Philosophy, which is from Yale. It means basically you did the classwork, now get on and get the doctorate done. A very interesting story with that, of course, is since it wasn't terribly important, I had them mail the diploma to me, and shortly after that, I received a letter in the mail saying, essentially, paraphrasing it, thank you, congratulations very much, please send the diploma back. And I went, whoa. Next paragraph. We basically found that our publisher of our diplomas had made a mistake. We'd like to correct it. And I think, oh, that's good. So I went back and looked at the diploma, check out what it is, and it's obvious right there. There is a very bad mistake in there. They let a Roman go ahead and write everything. Anyway, I did figure, well, rather than send it back, I'm going to save it because well, how many people get a degree that has a misspelling on it? And in case you haven't noticed, it's right here. There is no Republica of Connecticut. It's a Republica, as most people know. There's also one other feature about this Master of Philosophy I kind of like. This guy down here at the bottom, Bartlett Giamatti, had greater aspirations than being president of Yale. He went on to become commissioner of Major League Baseball. Okay. So what I'd like to do today is tell you a little bit of how we do research and actually mostly development from a small company sort of a perspective. We essentially go out, we're very small, we have 5 or 10 people, and we don't do large things, but we try and do some neat projects. Go into the, this looks like it's going dead, the folded imager, which is kind of one of our commercial products that we are involved with and trying to commercialize. And then also just a little bit on multi-sensor systems, but not too much. That's more along the lines what my business partner does. And by the way, if there's any questions along the way, feel free to ask any. Essentially, as being a small company, and especially in the turmoil of the times, it was quite a ride. We were incorporated by, basically the company was incorporated by David Brady back in 1997, but we began operation, as in revenue, about 2001. And now it's primarily myself and Ron Stack. We're located between Champaign, Illinois and out here. So we do quite a bit of things where we basically go out and contract to develop prototype systems for people, things that are a little bit difficult, that you want to do a proof of concept, but not necessarily get into production, as in selling very many of them. So we have a lot of expertise, basically in platform development. Ron's a double E, I'm a physicist. We do a lot of software development, a lot of optics, sensor board development, quite a few different things. And over the years, we've been able to get involved in a fair amount of fun projects. We've been in several DARPA programs, and primarily in these programs, we've been part of a team. So whenever I talk about things, think of there's a whole bunch of other people besides myself. This is not my accomplishments. These are a team of people that have been doing a lot of this. We also have had, from NIST, a SBIR, where we developed basically a optical coherence multiphoton microscope. There was a copy of something that the professor at University of Illinois had produced, but they wanted one that essentially could work and they can, at the NIST, and they could use for tissue development that they could count on working over time. So these are a number of the things we built. And of course, you don't see all the software aspects behind it, probably one thing kind of to point out is many of these, this one, and this one, are either multi-aperture or multi-processor systems. Sensor systems. And just again, as I said, being a small company, you rely on a lot of other people. So there's a number of people we go outside for to do our machining. We go to other companies for fabrication of the optics. You can see a large number of people we've worked with over the years. Again, part of this experience over the last 10 years, the fun part has been being involved with so many people doing interesting things. Okay, we're going to go back now to a few things that when we look at sort of the challenges or what we'd be interested in getting involved with, what are some of the criteria that we might find either challenging, what would be good to work on. And the term, if you haven't heard it yet, you'll probably hear a lot more in the future, is SWaP, the size, weight, and power of something, because mobile devices are essentially becoming a very important piece of equipment. How many of you here have a camera probably in your pocket right now? Most of you. I used to also teach a course. I also used to ask how many people had radioactive devices in their home. And somebody realizes, a few of you do, if you have a smoke detector. So all this technology that is kind of dispersing itself, if it hadn't been maybe for the cell phone camera, that there are billions out there right now, we might not have as much progress in doing some of the other cool things that we are putting together. Again, some of the aspects of this are the performance. For us, it's the functionality. What does somebody want to try and accomplish? That's a big point. So we have one project we're working on right now that's a gigapixel. We're working with a team on a gigapixel camera. So that is again, pushing the functionality by adding several sensors together into a system. Just coming down to the bottom, this is sort of where we're involved. We don't do every aspect of it, but we have our hands in certain things. The interesting parts we're finding is that, again, sensors, they're becoming so incredibly cheap. Why just use one in a system? Why not throw 10? Why not throw 100? Why not throw 1,000 into something? Because essentially the cell phone camera is really only on the order of $10. So you could put together a large system, if it wasn't for kind of this part, transmitting the data from one place to another. There's an awful lot of information in all those sensors. So we've had to come up to speed on all the various ways of getting high-speed information from one place to another. We do work with processing. Again, since we're proof of concept, we tend to work with FPGAs and other simpler systems rather than going to ASICs, because in certain cases, if you're building 1 million of these for a cell phone company, you can spend a lot of money on a piece, but if you're only making 5 or 6 of them, you work with tools that maybe aren't as efficient, such as the FPGA is efficient as far as power, but you can get a lot done with them. So that's kind of, again, quick background for distant focus. Again, we're driven by how can we make money off things, usually by doing research, of course, for somebody. And about 5 years ago or so now, we got involved with one of the projects, Montage, that was sponsored by DARPA, that was essentially asking the question, what could you do with the optics to do something essentially either smaller or different from the conventional refractive approach that you had before? And at that time, there were a lot of discussion, but one idea came out from Joe Ford and Eric Tremblay of UCSD of why not just flatten the optic, in other words, take the principle of the Cassegrain telescope and just add more folds to it, essentially a lot more reflectors into it, and make that into something that would essentially have at least a very much more compact form. On the left is sort of a conventional lens I pulled out of a ZMAX catalog. It's an f2.8, I think it's about 100 millimeter focal length. On the right is an f1 folded optic. I believe it's roughly the same focal length. You can see from the sensor size it's about the same. But the difference is essentially one is that you have reflectors instead of optics that are based on refractors, refractive elements, reflective pieces. And so one thing you can get away from is at least having all these doublets and so forth that have to compensate for the chromatic dispersion as they go through. The system itself is fabricated using single point diamond turning, so you can actually program the fabrication of the optic to have whatever size, whatever type or form of surface you want. So you basically get an A-sphere in. And essentially all these surfaces are aspheric surfaces in here. I believe they're up to, I think, 16th order polynomials that were designed using Zmax. The light comes in on this side, hits the first reflector, goes to the second, third, last reflector, and then onto the sensor. I'll come to this a little later again, but the fact is that only the surfaces are the important parts of this as far as doing the optics. So what is in between here could be air, it could be calcium fluoride, it can be any optically transparent material. And so there are choices to be made, but that, at least part of that gets away from the chromatic aberrations. So, and probably again, maybe stress very importantly, the length of this can be much less. We have essentially, with this 4-fold system, it's about 1/4 of the length of the system. Not useful in all situations, but for certain places where you don't have a lot of length, you're constrained by the length, such as maybe in a turret, for scanning something, that would be useful so you don't have that lever arm to move around. Okay, so again, the features are compact. It's one of the neatest features I found about this is if you make it in the right format, as in if you put it on a reflective surface rather than a transparent core, you can run this anywhere from visible up through long wave infrared. And so we have camera systems we've done throughout the spectral range. They're fast. This one here is about a f.7 lens, so you can make something very fast. In fact, you have to make it fairly fast because you put that entrance aperture way out at the edge. And okay, in practicality, you sell this as it's cost effective when it's molded. However, if you've ever done diamond turning, you know it's not, if you're making a few pieces, it's not so cost effective. So they're a little expensive to get ones of. If you wanted to do several hundred of them, thousands of them, you can get them down to $5 to $10 a piece. I'm not sure how many, I haven't even seen this in reality. I pulled these pictures off the web to give you an idea of how they go about fabricating the diamond turn systems. Essentially, I don't know if you've been in a machine shop or ever been there, there's typically a CNC type machine that, this one being composed of mainly a lathe that you put the piece of material on, and then you essentially take the tool and bring it close in to the material as it's rotating and remove the material slowly, but to a special form. The specifications are a little bit more than a little bit better, more accurate than a standard CNC machine. We typically prescribe about lambda over 20 or so. So you're removing very small amounts of material, and it can then take a bit of time. There's a lot more, to the part of this. They have to somehow determine what the wear of the tool is. They have to keep it in a temperature-controlled environment, etc. So it takes a little while and it takes a little expense in order to make a few of these. But on the other side of this, they also use this for a lot of germanium lenses anymore. I don't know if anybody does as many sort of the standard polish germanium lenses. A lot of them are done with diamond point turning because if you have a large number of them, you can slap one after another into the system. Okay, for the part of the design, I wanted to just mention again, there's a lot more, of course, to thinking about this and come up with a good design. And this is a very simplified approach of what you have to be concerned with. Let's see. Let me go back a couple. And here, let me just show you one thing. One thing you have to be concerned is that you keep the lights constrained so that one area in the design process, the lights from, say, this one coming in don't come onto the wrong mirror. That just leads to stray light. So there's at least a constraint that you have to maintain separation between all the annular zones. There is the, let's see, this is a look at a very simplified approach of what are at least the two fundamental constraints of light coming into the system. Number one is that after you enter the optic and then you are, it's transported to the second mirror, you got to make sure it bends enough so that it actually gets to the second mirror and then doesn't just go right back out through the front of the entrance of the lens. That is a limit given by this part here, this formula, and it's shown by this line here as a constraint in the what is feasible to make. The other constraint is that in the last bend, you have light coming, say, to this last mirror. You have to go back to the fourth and last reflector, in this case a fourfold, and then it's focused onto the sensor. You also have to make sure you bend there and get through to the next one without hitting the center too soon. And that's the other constraint, which is this red line in here. And this was in Eric's paper. I just wanted to point out that, so Eric Tremblay wrote a paper on this, but it turns out that many designs we do violate some of this because this is a very simple assumption we made, which was that all the focal power was at the very first lens. And as you might know, if you give a little extra focal power in here and then compensate for it with a negative lens later, you can get around that by bending it a little sooner and then taking it as a normal telephoto lens, taking some of that bend later. So we actually have done quite a few designs that violate that. Okay, over in that region there, and you can see that we've gone above. One other thing to notice, though, is that as you add more reflectors, such as the eightfold, the space that you can work with becomes a bit smaller. The two axes to be concerned about is that the larger field of view is to the right, so making a wide-angle folded optic is a little difficult. You just have too much spread as you come in, and getting larger apertures are also a little difficult because the larger your entrance aperture, the more you have to also make sure you bend around that very first part. Okay, how many have ever looked through or are familiar with telescope design and know a little bit about the Cassegrain systems? If you have a system that's based on an annular aperture, the spots you form are not the standard Bessel function description, the area function description you get. So that there's a slight difference, and of course it doesn't show up on here as well as on the screen, but the difference between a fully non-occluded aperture versus one that's, say, 80% occlusion is that there's a slight ring. You actually see the spots shrink a little bit in size, so it looks like it's almost sharper, but there's some extra rings around it. Again, because you have a slightly different opening, and maybe for those who are more familiar with the MTFs, this brings it out rather clearly. What happens is you end up actually getting at the far right a better contrast at higher frequencies, but you lose a lot of mid-frequency contrast in the system. Now, this could be a positive or negative selling point depending on who you are. At the bottom I put down the sizes of certain imaging pixels. And so if you're dealing with something such as we were in our initial work, where we were between 3 and 5 microns for the pixel size, it's having an effect, but it's not a considerable effect, especially around the 5 micron. By the way, most of the ones that we are fabricating are on the order of an 80% occlusion or so. So that bottom line is typically where we are concerned about. Most cameras, now the cell phone cameras, are getting out to about 1.5 micron pixels or so. So if you wanted to put it in that application, it would be a little more of a concern about the loss of contrast. How much of a concern? Here's a picture from one of our systems that we built, 5 megapixel camera, essentially some high resolution charts. And you sort of, in the blow up at the bottom one, you can see what happens when you start to lose that mid-frequency contrast. It's still, in some sense, it looks sharp but blurry at the same time. So in essence, you've lost some of the precision, you've lost some of the sharpness, the clarity of it, but you can recover some of that if you go back and do some post-processing to bring it back. As long as the MTF curve doesn't drop all the way to 0, there's a potential for getting some of that back. Okay, the pleasant part about the montage program was that we had the time to actually put together several systems. Not just one, but 3. We had only planned on 2, but they actually gave us a no-cost extension to do a middle one to approve a little, something extra. The lens on the left is a conventional refractive lens. I believe it's on the order of the same focal length as the one next to it, which is called the 8-fold. This is a little bit difficult to see. It works now, but that little silver area down at the edge, that's the annular opening. That's the entrance aperture for light into this. I do want to mention also that in building this CDM optics, I believe went ahead and fabricated the first one. We built, at Deficit Focus, we built the electronics for that and packaged it after that. So you can see barely that this is very much thinner than the optic over here. We went with an 8-fold so that we only had to be diamond turned on one side. So there were 4 surfaces that were aspherics, and then the other surface was just a flat. The Nano, which was our intermediate proof that we could do a little something more for the DARPA manager, was actually a section of this, and I'll show you the section of it later, so that essentially the aperture is over here on this side. It's a part of this optic, and the sensor is down over here. And then finally, the very last one is a 4-fold, which we described as the quad, which has about, let's see, I think it's 13 to 15 millimeter focal length. The optic was about 5 millimeters thick or so. And the package itself, including sensor and most everything, was only 10 millimeters thick. Again, back to the Nano again. Again, one of the neat features of this optic is it's like you can slice something out of the whole lens. You don't have to have the entire lens. In fact, the nice part about the optic itself, if you only have a small part of it, your PSF can become a little bit better and your depth of focus becomes a bit better. So we essentially took the 8-fold that we had, took a section out of it, and then packaged it with a sensor down on the, I'm not sure if you can see down in here, okay, there's a sensor here, onto the optic, and included a USB connector inside. So this is an entire camera in the size of what was at that point a popular Apple product, the Nano, which is where it got its name. So it was essentially the same size, only it was a telephoto lens and a very small package. The next one we did, the third one of the montage program, was a real fun one in that it was basically had aspheric surfaces on both sides. So essentially it was 4-fold in that there were 4 different folds. The optic, let's see, so the entrance is on the very edge. This is just kind of frustrating. It's kind of on and off. Okay, maybe it's just loose. Nope. Okay, so it came on this side here. It was at least one place. This is the entrance all around it. It's actually made of 2 different pieces in this case, so that we only had to have one side diamond turn. The reason being for the middle spacing in it was so that we could do a squeeze focus. In other words, most of the time with the cameras that you have, conventional camera, you either move an element or you could move the sensor with respect to anything. By changing the spacing between these 2 elements, we could also do a focus with this, although it wasn't a very large difference in focus. So we had, I think, on the order of it says 20 microns, I think I remember a little bit more, that you could squeeze and change the focus. Unfortunately, again, in practicality, some of these things sound great, aren't so great. If you ever use index matching material, index matching, we didn't use oil because we didn't want to have to be concerned with keeping that in one place, so we used a gel. And if you have something that's only about 100 microns over a large surface area, you find that the gel does not want to go where you want. It doesn't mind being squeezed, it does not want to flow back in. So again, part of the learning process, as I was mentioning earlier, part of this is failing as fast as you can so you get to learn a lot more. This is probably what we might consider a learning process, and that squeeze focus was not the best for at least this configuration. Point you to some numbers. Actually the F number is about 0.7 on this. We usually describe two different values. There's an F number that's sort of the conventional aperture divided by, or the other way, the focal length divided by aperture, and then we have what is effectively what it would do if it were a clear aperture lens. So it's a little bit slower in that case, but F1 is still pretty good. Okay, and the two pieces up in this corner show what they look like before the reflective material were put on. The material itself is calcium fluoride. Just so you know, the fabrication is very difficult with conventional glasses because conventional glasses, I guess, they shatter, they fracture, they want to be polished, they do not necessarily want to be tooled. So you only have a limited class of optical materials, this one being calcium fluoride. And so we did that one with calcium fluoride. And then again, sort of the pictures, the glamour pictures of all of them. Probably the point I would like to make on this is that we put together a system that had not just one of these quad folded imagers, but 7 of them together. The program was not just to change the format of the optic, but to also go to either wider field of view with higher resolutions, etc. So we had to we spent a considerable amount of time doing the electronics. And that's probably, again, one of the most kind of enlightening things as we go along with all these is that as much fun as all the optics can be, there's an awful lot to getting information on and off the sensor and into a computer. This is again, the four-fold quad imager. It works again. Again, the back side of it is just a flexible circuit that's attached to the sensor. Pulling that out, we have some elaborate or some pieces of Ron could tell you better about all this. Essentially, they could separate the two pieces to a good accuracy and maintain that. Just to give you an idea, again, of the tolerancing of it, this one part and this part had to be held, the two pieces of optics had to be held to about 10 microns or so accuracy as you were squeezing and changing. Otherwise, you'd have a considerable change in the spot quality. Just a quick thing, once you get some of these things and put them together, the one thing you want to do is go show it off. This is what we did. We went out with Joe Ford into the desert for a place, a company, agency probably that doesn't want to be named, asked us to demonstrate it for them to see what it would be like, especially in an environment that wasn't so pleasant, like 127 degrees during the day, scorpions, rattlesnakes, all sorts of stuff. And they asked us to bring this thing that was designed to work in a conference room, as in the focus range was sort of on the order of 2 to 5 meters, and see if we could do it somewhere out at 500 meters to a kilometer. Because they'll understand. They just want to see, again, is this stuff real? Proof of concept is cool, but you want to see some of these actually work in the field sometimes. And as you can see here, I mean, this is zooming in on some of that area. Again, you're losing some of the quality of the contrast, but we were happy that after several hours, we were still getting this thing to work, and it was providing good, relatively good pictures, even though they're not, great pictures. It wasn't designed for this. It was a proof of concept system. Now I'm going to slightly change to some of the theoretical aspects of this again. One of the cool things I find about the folded imager is, if any of you are photographers out there, you know what the term bokeh stands for, or however it's pronounced. That is, when you go out of focus, things can have an interesting PSF or whatever as it changes. And for the folded imager, instead of going from a spot to a larger spot, you go from a spot to a ring. So this is going through focus. Again, this was about 100 millimeter focal length optic. And as you can see on this one, if this is a perfect system, this is a simulation, you get it going from a spot out to a ring. At first that seems like a really awful thing, but until you go to do tolerancing on it, checking it later. And that is if you, again in simulation, look at it, if you look at a decenter, so this is about a half a mil or so decenter between the two parts, you get some pretty unique shapes out of this. And if you have a tilt, you get a slightly different unique shape. And this turned out to be actually a cool thing for us because we built a thermal lens to work with a thermal camera, whatever, but we could attach a visible spectrum sensor to it. So when we got to the end, we noticed we had built this thermal lens, and we thought, the performance isn't quite as good as we thought it could be. We took off the thermal camera, put on a visible spectrum, and we saw some of these things, and it was like, aha, we have one part of this package, there's a screw that's on too tight, and it's pushing it and compressing it on one side. So again, maybe a sort of interesting, unique, you wouldn't want to do this all the time, but the fact that it's cross-spectral let us do some extra things with this. Okay, here's something that came out of CU, the idea of wavefront coding. Okay, the idea, let's back up a second. Remember I told you that some of these lenses were a little fast, like f.7, f1. You can calculate now, right on your desk, what the depth of field is for that. It's not very big, is it? It's very limited because you essentially have all those rays coming in at a very sharp angle. Okay, so one aspect or one approach to trying to make that, minify that effect is to add a phase-encoded structure onto one element. And this was demonstrated by putting a phase-encoded structure on one of the optics. This is on this side is the one that does not include any phase encoding. The target has a variety of elements at several different depths. Again, this is in the lab. In this one, you have a phase-encoded image before and after the processing. So what you're supposed to see here is it becomes sharper after the fact that you put the phase encoding in. Truth be known, there's so many issues with the fabrication that there's also a lot of differences between this one and this one in just trying to do the alignment. Again, you were trying to get 5-micron alignment so that everything wasn't necessarily standard. We were fortunate in having this one definitely work better so we could show that phase encoding would be a useful thing to include in this. And for those maybe of you who don't know, the phase encoding is just a slight deviation from the A sphere. This one was a cosine 3 theta, r cubed, I believe. So it was probably on the order of 1 or 2 microns. So they had to just have a slightly different process for doing the fabrication on the diamond turning. This one just says the same thing. Essentially, we didn't do it in real time. The one thing we do have fun sometimes doing is when people ask us to take a camera, they expect maybe images, and sometimes we turn them into video instead. So we were actually doing some of this embedded in a MATLAB routine, and we could get a few frames per second out of this. So I guess another life lesson for you, if you have a sponsor ever, sometimes overpromising is good, and over-delivering is even better. So that was kind of the fun part with doing the extended depth of field. Okay, let's go back again to the hidden parts of this. I mentioned the folded imagers, kind of the cool optic part of this, but behind here is this box. This is actually a system of 7 folded imagers that are put on conforming. It was basically, we called it the basketball, or part of a basketball. They would each look out in a slightly different direction, and they would bring all the images together, and we'd form a mosaic from them. Okay, to do that, we needed a box, because Severn cameras, I don't know how many of you have ever checked out on the market. There's very few cameras you buy that have basically the ability to add several of them together. It's usually some custom system that you have to do to get the information. And if anybody tells you you can do it all via USB, yeah. Most computers, at least at that point, couldn't really just pull in everything off a USB interface. So this box here is an FPGA inside, and it would take all the image data from all those 7 sensors and bring it in the box, and we'd do a lookup. We'd put them together into one simple mosaic image. And I think it worked the night before the demonstration that we had for the final program review. So it was a very elaborate process. Let me just mention, I mean, there's, again, many of the things we don't think about is that you have to, usually typically go from a Bayer to an RGB interpolation. You got to do white balance, gamma correction. If you have any convolution, we had a lookup table to match everything together. And then we had to provide sort of a dynamic zoom capability. So a lot of work, a lot of effort, but this is probably, I'm not going to get into this as much, but again, the idea of the multi-sensor camera is there's a lot in the box behind it. It's not just the optics itself. Again, a lot of features going on. So what do you do when you end up having some fun stuff like this? As you might know, you could publish it, right? You have to get it out to all those respectable journals. And so Joe Ford got it into Popular Science. And he did it not only once, but he did it twice. The idea of origami optics. At that point, they basically were selling it as a wonderful optic to put in a cell phone camera because it was so flat, it didn't take up any room, and you could put telephoto capability in your cell phone. Okay, what do you really do with it? Obviously, you can do that, but it's the margin on some of the cell phone cameras and what they want to do is a little bit more intense than that. Essentially, you try and sell it as a compact, long focal, or telescopic type optic. You can make it very short. F1, there's not very many optics you can get between F1 and F2 of those sizes. You go to some place where you can't build many optics, at least not cheaply, or you don't have very many pieces of materials you can use, such as up in the long wave IR and the mid wave IR. A great place to work there because, again, you're working with germanium and some other systems. Now we're still reflective, and we can also extend this down into the visible just by having the right coatings, gold coatings, silver coatings, etc. We have people that are interested in a star tracker. These are the things that go up in the satellites, essentially for doing the navigation and alignment. You might ask what's wrong with the current star trackers. They have systems up there that go into like the Ball Aerospace just down the road. They have several. There's a new category of satellites coming out called microsats, or maybe even nanosats, which are essentially very small. I think they're on the order of, components are 100 millimeter by 100 millimeter. You're not going to put a star tracker that has a very large lens on it in that sort of a system. So again, there's that. We've been working with somebody on a star tracker, how to put that together. One cool feature which we haven't really pulled out and done anything with yet, we have the ideas we haven't demonstrated, is that you remember that large annular aperture, that's a nice little gap that goes around. You could subdivide that and put something different in each piece, and then put some sort of a spatial light modulator in front of it so that you sample it differently at each piece at every exposure. Anybody hear of compressive sensing, compressive imaging? There are the idea that you could probably, by sampling several times fast enough, you might be able to make a hyperspectral camera out of it. You might be able to do other interesting things. And we haven't done a lot with it, but again, the feature that's nice about it is your aperture is round, long, and sort of linear. So there's that aspect you could use. This one we won't go into very much, but watch for something in the next few years, I guess. We'll see how that works. Someone's got an idea at UCSD about putting it in a contact lens and looking through it directly. So you would have basically embedded zoom in there. And I won't go into any more than that, but this is part of, again, a program that I'm not as, I'm in another aspect of this, but it can show where the folded imager could go. And again, as I'm saying all this, the idea is not just the folded imager, but what happens if you consider different materials, different ways of machining and doing things. How can you get away from the old paradigm of refractive elements? This will take a few seconds to load because it's a complicated diagram. Okay, the other nice thing about these is that you can stack them. If you have an annulus and you make one smaller than the next, you can have a stack of imagers, one on top of each other, which is a great thing if you want to do co-imaging of something so that you don't have to worry about the fact that you've got a displacement between cameras and you have parallax. Okay, so let's just I'll move along a little faster here. We did this with MITRE, where essentially we took the montage camera that we built and we were going to basically combine it with a thermal camera so that we could do imaging of two parts of the spectrum at the same time. A quick note, I'm going to come back to the core material for a second, and I'm sorry that it's probably difficult to see some of the ZMAX stuff on the Macintosh presentation. All of these across the top are essentially the same surface profile for a lens. The only thing that's different between them is this one's filled with air, this one's filled with calcium fluoride, and this one's filled with germanium. And the difference you can see actually is up here. There's a wider field of view for the germanium because essentially you've got the refraction that occurs when you enter. It refracts down to a shallower angle. So as long as you stay in the material after that, you essentially have a wider field of view. The problem, of course, then, is if you have any dispersion in the material. Calcium fluoride's not so great unless you want to pull out your spectral information either by the different colors, color filter array or whatever. Germanium's not too bad. Again, this is kind of cool, about 0.25 or so for that. These are, I can't remember, I think they're about 100 millimeter focal lengths. These are all designs, not actually built. Okay, I'll move along a little bit through this. Essentially, hollow core, solid core, we've done both. I like the hollow core. Hollow core means there's air in the middle. That means essentially you don't have to worry about the index matching material. You can change the focus however you want. It's a little easier, and you can also use materials such as aluminum. We use thermally stabilized aluminum to put these on. And the camera itself, again, this is from MITRE. This gold part here is the reflector for the first part of the folded imager. This honeycomb here in the middle is the montage, and one of the things I didn't mention earlier is that these things are very susceptible to stray light. Once you get light in here, everything, essentially if you looked at these surfaces, well, the surfaces right here, these are two of the surfaces that are in that part. So you got two, let's see, this would be the entrance aperture here, this would be the back aperture with the sensor here, and they're held with a spacer about so far apart. The main thing about, you might notice, these aren't coated yet, but they're all reflective surfaces on the inside. So you've got to be fairly careful about the light and how it gets in. Otherwise, you end up with a lot of stray light all over, which bleaches out the rest of this. But as you might guess, if we're looking at this for star trackers, we've got some ideas, some good ideas about how to take care of that. Pictures, that's the system. The interesting parts again, focal length here, 164 millimeter focal length and 27 millimeters. So it's much more compact. f.7 for the, this is visible spectrum sensor, f1.3 for the other. We basically matched them up so that sort of there's a 2-to-1 pixels. Each 2 pixels, I believe, in here would match 1 pixel with this one. What does it look like? Well, if you ever have young kids that want to sneak up on a van with their toy weapons, a visible system works really great. You can see through polyurethane and other contrived little experiments to show what's going on, but this is essentially the thermal pictures. This was a 640 by 480 camera. Again, here's one thing I want to point out. See that little, that's a pole in the back. That's part of the boku that because of that ring-like shape, then it's out of the depth, out of the field that's in focus. So it's kind of interesting there. Another example, this was the picture that was a wider field of view for the visible spectrum camera, and then this would batch the two together. So if you needed to, for some reason, pull out some information with respect to each other. Whoops. The point here on this one is just, we built something for the long wave IR. We tested it in the visible. So its MTF isn't as good as it could have been, but we didn't specify it to that sort of quality when we had it fabricated, but we were able to use it there if we had wanted to. MTF's just, again, some through focus on this. I just like the pictures. Okay, the honest part of this. What is it, the drawbacks? Because you don't often always hear about everything if you're trying to sell this, but there are drawbacks. There are things, and you mentioned, of course, the ones you think you've solved. So, shallow depth of field. Yes, that is an issue. Any camera that you have that's f1 is going to have an issue with a depth of field. We've shown, that, okay, if we use some wavefront coding techniques, that's one way of getting around it. Reduce field mid-frequency, and contrast in the MTF. Again, you can get some of that back if you went in and did some digital post-processing. Stray light, any reflections? Actually, in this one, you can see a small gap between some of these. If you put little structures in there of the right size, right shape, you can at least get rid of a lot of the stray light, and you can also put a small structure in front that it turns out to be part of the front surface that can take care of a lot of the light coming through. One of the biggest issues we did face, though, is that when we went to integrate these, most of your CMOS cell phone sensors have micro lenses on the front. Many of the CMOS sensors try and concentrate the light so that it fits into the pixel, because most of the pixel is not necessarily photosensitive. There's a lot of wiring in between. And so they're usually designed for a certain chiffre angle as they can come in and to get as much light as possible. And you can see from the simulation here that we've got some pretty large angles coming in. So that was actually one of the good things about index matching, is we put that in and it got rid of the effect of the micro lenses. Okay, now I didn't expect to have too much time left. I'm going to shift gears just quickly and go through some of the multi-sensor system and get through this. As I was telling some people, my background is actually particle physics. Why is this interesting? Well, I just want to point out, this is the stuff that got me excited when I was a kid. It's a photograph. There's this great big monster. Here's a guy here. But this is a monstrosity that's just essentially filled with near boiling hydrogen. And at the correct instant, when they throw some particles in, essentially they drop the piston and get everything to boil along the tracks. But again, it's a camera. It was a simple photograph. It then took forever to get the information out, because you'd have this room full of staff that just would measure them. What is modern physics, particle physics detectors like? Well, here's the data stream on this side. So you can see one reason why you're not going to get the same effect out of a bubble chamber. In fact, I love the name for this. They call them time projection chambers. And when I was in there, I was like, ooh, how are we going to project time? Well, it's related to the drift of the particles through them. The main thing is, look at here, all those sensors, electronics, things at the very center. I love that cool picture that someone put there for that. Basically, there's electronics anymore. In fact, we don't take the picture anymore. We take, they don't take the picture anymore. It's the information about the tracks that are important. Again, going along in my history, whoops. I used to work for this large telephone company called Bell Labs, and they made what was at the time one of the larger digital systems in the world. It had 100 million lines of code. Essentially, it was in place there to take poor tortured souls so that they didn't have to route the phone calls anymore. But look at how much capacity, roughly, just an estimate. It could handle about 100,000 trunks at about 64 kilobits per second each. That was 6 gigabits per second. Actually, billing was one of the more critical features with this. They wanted to determine how to bill everybody for it. So, a little side note there. But so processing essentially was an important thing. Now let's move forward a few years, but still back about 5 or 6 years ago. We put together a system which was based on 128 sensors essentially were low resolution, and by combining them, because each image had a little bit of disparity with respect to the others, we could build a higher resolution image out of it. This is the front of the system before the lenses went on. This is the back of the system. Electronics everywhere, connections everywhere. This is a small PC-104 computer, I believe, that was used to collect all the information. And then there was a remote computer to take that off and put it all together. Okay, so this is sort of where we see a lot of at least the high performance systems starting to head. They're no longer just the camera or simple sensor or whatever. They are little mini data processing centers. And the optics, that's just some boring little part that you throw on the front. No, there's a lot more to it than that. Anyway, here's some of the results. Again, this is an image from one of the detectors. This is from the combination of about 40 of the sensors. So you can see you can get what at that time you might call super resolution. It's enhanced resolution. We could put together several of them. Now, rather than talk to you about multi-sensor systems, please go back and see Dr. Brady's talk again. He covered a lot of information there in the terapixel imaging. However, let me just show you a few things. This is what my colleague Ron Stack is dealing with in helping them to put together a 2 gigapixel camera. This is the backside of the camera. And it's not even the full backside. It's just a part of it. This is the wiring that you have to take from 200 sensors to get to another set of, and it's not shown here, set of boards that are going to collect that data, store it temporarily, and then allow it to read out. And I wanted to contrast that with okay, here's a 140 megapixel sensor. Obviously you can make large sensors, but the optics with that wouldn't probably fit in as small a size box as this might have to. This is sort of 2 feet on the side. And when they put everything together, about another 2 foot back from there. Again, important parts. There's a lot of data manipulation and processing going on in this. And if you're going to take hundreds of thousands of sensor chips to get to gigapixel cameras, you've got to worry about a lot of things that really haven't been worried about before. Power considerations. Most of these sensors, if they're on all the time, are usually consuming 100 to 500 milliwatts for the sensor alone. Okay, 1,000 sensors or a few thousand, you're up to a kilowatt in that little box. And that's just for getting the sensor going. Now you have to pull it off the sensor into some data routing system. Okay, say if you want to do 10 frames a second, most of the people are going to be interested more than just 1 frame at a time. 10 frames a second at, well, let's see, say a gigapixel per camera, 8 bits or so per pixel. You're not far away from hundreds of gigapixels per second. Okay, so you've got a lot of complexity in the back end. And what are you going to do with it? Are you going to store it? Are you going to put it someplace where people look at? There's a complex system to putting all that together, to even using that data. So again, I just want to, from distant focus's at least aspect perspective on this, a lot of the fun stuff is the back end where you're trying to deal with all this data, how you put this into a system, and then how do you put this into a system that goes on someone's head. This is, on the left is not ours. I found this on the web. I was looking to see what was out there about the Scenic CEV project, and they talked about essentially a Terminator vision that they could put on a soldier's head. And I think that the proposal for the Scenic is much ahead of them. Usually science fiction seems to go ahead of what people expect. And so anyway, this system here is one of the parts of the Scenic project that we're going to be looking at, which is how do you get something that can put very high resolution imaging into a very compact, low power package and operate it quickly and give it to somebody who really has other things on their mind rather than taking a picture. You want to enhance what they're doing. So just again, an idea in here, there's a few tens of sensors, somewhere between 25 to 100 megapixels. It's going to be battery operated for about 24 hours. That means, essentially, that's part of the, I think is about a 250 gram package or so. So again, never be satisfied, push ahead to do the impossible. That's kind of the DARPA way of doing things. So a lot of things going on there. But let me just summarize because we're coming to the end. Okay, the points I want to make point out is at least with the fabrication techniques, there's a lot of new things you can think. You can kind of take your mind away from what was sort of the usual stuff, or you can say you go back if you consider the fourfold and the folded imager as similar to a Cassegrain. You can do things better, differently. You can approach things differently, and they can lead to new optics configurations. On the other hand, also, all these sensor platforms are getting to be little data monsters with lots of data in them, and the user is really concerned about making sure that they can carry it around, that they can use what they need of it, and that it doesn't basically take their cell phone down to zero power in no time at all. So I guess the part I like about, again, being in distant focus is just the fun part of working, trying to develop this technology and working with a lot of people like you guys in here and other companies in the area. And so we're having a lot of fun, and you guys, if you stay in the field, you got a lot of fun stuff to look forward to.
How does the Cassegrain folded lens scale to a gigapixel camera? So it looks like in your prototypes.
Right now they're separate.
Okay.
Okay. It would, most of the gigapixel cameras want wide field of view. So you might consider putting it, I didn't put the picture in, that each of these gigapixel cameras have little cameralettes inside, little wafer scale cameras. Generally I would say that's probably not that's not a good mesh. The folded imager works better for certain other things. So again, maybe like the in-eye zoom or things of that sort.
In your prototypes, so I thought I saw several megapixel imagers.
Mm-hmm.
Is the point spread function well matched to a pixel?
That'll be an important thing, yeah, because they want the resolution. This is the start of this project. So this is sort of in the looking at various candidates. The cool part is we got a lot of fun, a lot of good team members looking at various aspects, not only just from the optics side, but is there any computational imaging that also can be used to take down that number of pixels? I mean, obviously one thing is to reduce the number of pixels and still maintain the resolution. But this, I don't have much to say about this yet. So you'll invite somebody back next year and they can tell you a little more about it. Yes?
Is there an advantage of having more than two aspheric surfaces in the multiply folded thing, or is that, can you do chromatic aberration compensation on that?
Let's see. One thing I didn't mention, you could probably add some diffractives in there. I mean, you could make the folded imager a diffractive. Boy, would you throw in chromatic aberrations like crazy, though. Most of the trouble with I get the chromatic aberrations coming in from that very first surface right now. If I use it in, say, calcium fluoride or something of that. As far as the number goes, there seems to be a minimum number depending on what you want to do, how wide your field of view is. So I found that if you go to very wide field of views, which isn't very much for the folded imager, you'd like to have 4 to 6 all aspheric surfaces. The fewer, there's some limit that you can't necessarily go down below, it seems like. I don't have the theoretical information on that. I think most of us know, or had seen, that most telephoto lenses don't really have a lot of surfaces compared to some of the wider field of view. So the problem of, if you go to a wide field of view with a folded imager, you have to go maybe 6 to 8 surfaces, which makes the whole thing really a mess to control the ray distribution on the inside.
But what is air fill?
You don't need chromatic correction there.
Right, so then is just 2 surfaces enough?
No.
Still not.
Well, it depends. If you have a very narrow field of view, yes. If you get, depending on your width, the wider it is, you just seem to need more. My background is not optics, so I can't give you I can only give you sort of the version of what I played with ZMAX. It seems like, well, even the Cassegrain is actually 3 surfaces, because you have the 2 mirrored surface well, maybe it's not the Cassegrain, but the enhancement of that has the front surface that actually does is an A-sphere or something like that. I can't remember. So there's 3 surfaces and even maybe it's a Cassegrain Schmidt or something like that. So there seems to be a minimum number. So.
Any other questions? So let's.
Your gap focus, and I just got the table, it said you were changing plus or minus 20 microns, and it said the focal length was going between 3 and 10 meters, which seems like a large range for only 20 microns or 40 microns of motion. Is that right?
Let's see. It's a 4-fold, so actually it's 4 times whatever it was. So you get that much. So that takes it to 80, and it's a fairly wide angle. So if you were more of a telephoto type, in the telephoto regime, it's not going to go as well.